All right, let's talk about logistic growth. And hopefully you watched the exponential growth and decay video already. You understand what exponential growth is. This, my friends, is one of my favorite topics because it starts to get right to the point where calculus actually starts to really describe what happens in the world. All right, so if you think about exponential growth, sure, it happens, and there are some things that exponential growth describes perfectly. There's nothing wrong with this model. Right? Exponential growth says that the rate of change of the population is proportional to the population. And it says that start out with a population of rabbits, and all of a sudden, boom, it takes off and it goes up forever. There's no bounds here. Well, this does accurately describe your bank account. Put your money in a savings account that gets you 4%. This is perfect. It doesn't matter if it's 5 years, 10 years, 5 months, 500 years. As long as this rate doesn't change and the bank doesn't collapse, this is perfect. However, lots of times in books, we'll talk about exponentials and it will describe the population of a city or the growth of a company or the population of rabbits in the woods. This is not realistic anymore. This is unbounded, unchecked growth. You can't stick 10 rabbits in a forest and honestly expect them to grow forever now with 1 million rabbits. There are other factors involved, and that's, boom, what Logistic does. Logistic adjusts for other factors. And so let's look what it says. It says dp dt equals kp. So the growth rate is still proportional to the population, but there's another factor, m minus p. So k is still this growth rate, and m is the carrying capacity. The carrying capacity of the environment or of the economy. Again, we can be talking about a population of rabbits, or we could be talking about the growth of a company in the US economy or a different economy. Again, there are only a limited number of resources. Let's talk about the rabbits. Okay, take a rabbits in the woods. If you get too many rabbits, you're going to run out of food. They're going to be way easier for wolves and owls and foxes or whatever's hunting the rabbits to eat. There's disease that's going to come into play. There's all sorts of things, so that the environment only can really support so many rabbits. That's what this capital N represents. It represents kind of the ideal population that the environment, whatever the environment is, based on the size of the forest, the predators, the resources, the weather, all sorts of things, can support. Okay, and then the growth rate is just probably more dependent on maybe the species or things of that nature. And so what does this curve look like? Well, this curve looks like this. Let's put a dotted line for the carrying capacity. That's what the population is going to support. So let's start here. So let's start off with like 10 rabbits. And if you think about it, look at this equation, dp dt, the growth rate, right? Or in this case, it could be a decay rate. If the population is less than m, this is a positive number, k times p is positive. And if p is less than m, m minus p is positive. So a positive and a positive make a positive. So we have growth. And it's an accelerated growth, and it looks something like this. It looks just like exponential. But then as we get closer to the carrying capacity, our growth rate actually tails off. It still grows, but not as much. And we get something that looks like that. We get the logistic curve. Okay? This is logistic growth, and this differential equation describes the slope, the growth rate of it. Now, if you had a population up here, okay, so this was like, what if the original population was 10 rabbits and the carrying capacity was, I don't know, scale that, 120 rabbits. What if your initial population was actually 150? Meaning, how'd you get that? Well, I don't know. Somebody took a whole bunch of rabbits and they chucked them in some woods. The woods can only support 120. What's going to happen to the population? Well, they're going to die. Not all of them, but they're going to decay, and it was going to look like this. Again, those are the solution curves of this differential equation. If you have less in the carrying capacity, it's going to grow. It's actually going to grow faster at first and then tail off and approach this value. If you put in more rabbits somehow the population got too big, and then it is going to decay to reach this carrying capacity. Think about if P is bigger than M, this term is a negative, and then you get negative rate of change, which is a decay. Okay, some other things we can look at. They fool you with all of these things. They ask you like the limit of dp dt as t goes to infinity. Okay, how would you answer that? Well, what's happening to the growth rate as time goes to infinitely big? Well, eventually the growth rate goes to 0. It doesn't matter in either case, the blue case or the red case. Eventually the slope becomes 0 because eventually what happens to the population? That's another question I like to ask. What's the limit of the population as time goes to infinity? Well, that's just the carrying capacity. That's the definition of the carrying capacity. It's what the population will approach eventually because of the resources that the typical environment or economy can support. Okay? And so we have capital M and 0 as our limits. Okay, other things we can look at. Well, it would take a decent amount of time and about at least half of this sheet if I solved this differential equation. Now, getting it ready to solve is easy. Again, this is a separable differential equation. So if I took this, I'd get dp over p times m minus p equals k dt, right? It is a separable differential equation. I separated, sweet, and I integrated. Now this part, however, you look at it, you're like, oh man, it actually requires partial fractions. So if you're not in Calc BC and you're watching this video for fun, then you don't know what partial fractions is. Okay, partial fractions would take a little bit, and so I'm just going to tell you the answer, okay? And so if you solve this, you're going to get P as a function of time, right? That's what we're solving for. If you solve a differential equation, you're finding the function P, and it is a function of time, and it's going to equal this. M over 1 plus A e to the negative kmt. Okay, that's what you get. This equation is linked to this. Just like this equation, if you solve that for time, you get this. Okay, this is the exponential equation that relates back to the differential equation. This goes with this. If you tell me K and M, I'll tell you this. So what's this A stuff? All right, let's go back to the original problem. How would I find A if I knew an initial population and I knew M? Well, A is not the original population. A is a number that makes this happen. So let's do this example, okay? So let's take the example that M is 120, okay? K, let's go ahead and make K 0.1, and then P naught is 10. Okay, those are three things you have to know in order to actually find the equation as a function of time, because I got to find A. So plug in these values. So I know that this is true when t equals to 0. So I know that the population is 10, the carrying capacity is 120, 1 plus A, and then the nice part is it doesn't even matter what K and M are, because this is e to the K M t, but t is 0, so this is just e to the 0, which is 1, so I get this. Okay, so what must A be for this statement to be true? 120 divided by what equals 10? 120 divided by 12 is 10. A must be 11. Okay, so these values here allowed me to find A, and now I can find the particular equation that describes this scenario. P as a function of time would be 120 over 1 plus 11 e to the negative km, or just take k times n, so I get negative 12t. So I actually have an equation that describes this curve, right? If you graph this on the calculator, you're going to get this exact same thing. Okay, so solving this, well, again, you don't have to go through this whole partial fractions thing. Once you know that this differential equation is logistic growth, then you know that this means this. This information can tell you the particular solution with the details. Again, you find A using the values. Okay, A doesn't represent anything other than it's the number that makes D is a true statement. Okay, what else do we want to talk about? Well, in logistic growth, again, it's beautiful. If you're below the carrying capacity, it's going to grow. If you're above the carrying capacity, you're going to decay. But there's a point here that's kind of important. Okay, now what's important about that? Well, hopefully you can see that it's the steepest. The growth rate grows, biggest growth rate right here, steepest, and then the growth rate tails off. Again, once your population gets close to M, once P gets close to M, then this is going to be a small number and the growth rate was going to decay, and that makes sense, right? If you have 120 or 110 rabbits, you're pretty close to the carrying capacity. You're not really going to jump and grow very much per year. Okay, you're going to grow the most, not at the beginning. Well, because at the beginning your population is small and your growth rate's still proportional to the population. You still got to get a decent population and then you hit that growth rate. So I do want you to know, when is dPdt the max? And it will turn out when P is half the carrying capacity. Okay? Half the carrying capacity, and you can think about what this looks like. And I go, this is going to be an interesting graph. You've probably never graphed this before, but if you look at the graph of dP, dt, not versus T, but versus P, how does the growth rate change based on the population? Well, when the population is 0, you have a 0 growth rate. Okay? And when the population gets to M, you have a 0 growth rate. But if you multiply this out, can you see this is going to be a negative P squared? So it's just a parabola. So we want to find the maximum slope. We want to find this, and we all know that parabolas are symmetrical. So it has to be at half the carrying capacity. Again, that's a fact you now know. I just proved it to you, that when the population P gets to half the carrying capacity, that's the point where the population is growing the fastest. Now, it still grows afterwards. It's just not growing at a bigger and bigger rate. The growth rate is slowing. It's still positive. Same thing here. The growth rate is positive and it's increasing. Now the growth rate is positive and decreasing. And again, I really like this graph because you're looking at dP dt versus P, not time. Again, dP dt is a function of the population, except if we solve that, we get the population as a function of time, meaning how many rabbits do we have after 1 year, 2 years, 3 years? This tells us that. This can tell us the growth rate given the population, but it's not a function of time. This is a function of P, this is a function of T. Okay? So there's some other things they can do with this that kind of trick you guys up. Okay? So what if they just tell you this? What if they tell you that dP dt equals 0.2 P times 50 minus P? First, do you know it's logistic growth? Yes, you know it's logistic growth because the rate of change is proportional to the population and the difference between the population and some carrying capacity. Again, you know that this is K and this is capital M. And you know it's logistic because it fits the form. All right, they like this one too. What if they gave you this? What if they put it into that form? Do you recognize that this and this are the same thing? The growth rate is still proportional to the population, and then if the population becomes 40, oh, I jacked that all up. I didn't mean to do that. Erase. That was supposed to be P over 40, my bad. Okay, so the growth rate is still proportional to the population, and 1 minus P over 40. Do you see that when P equals 0 and when P equals to 40, we still get a growth rate of 0, which means this is your capital M. And you can see that. Just multiply this by 40 and divide this by 40. And again, if I have two things, I have this, and I don't want to change anything, I want to multiply this by 40 to make it 40 minus P. Then I just have to divide this by 40, 10 over 40 is 0.25. And all of a sudden then the red, again I apologize for that silliness, the red differential equation looks just like this, and now they're the same. Again, once they're in this form, then it's really easy to see that this is actually K, and this is the carrying capacity. Okay? If they give you some equation, maybe they give you this. Maybe they tell you that P of T equals 350 over 1 plus 4 e to the negative, I don't know, 0.1 t. Maybe they tell you that. If it's in that form, you know it's logistic. So what do you know from that? Well, if you remember the formula, you know just looking at that 350 is m. What's the initial population? I don't know, figure it out. Plug in t equals to 0. When t equals to 0, this is 1 plus 4, and that's 5. 350 divided by 5, oh man, what's that? That's going to be, what, 20, what, 65? I think 65, let's hope. So you know the initial population is then 65. No, 65. 5 goes into 120, 60, no, 70. Wow, that was the worst math I've ever done. 70. Okay, the initial population is 70. I knew 65 seemed wrong. There's no way there could be a 5 there. The initial population is 70. Now again, this point 0.1 job up there, you know that's equal to K times M. But if you know M, then you can take 0.1 divided by 350 to actually find K. Again, they can give you differential equations in different forms. This is the classic form. We know that the classic dp dt equals Kp times m minus p is the standard logistic formula, but this red is the same version. It looks just like this, it's just rearranged. They could give you this. We know that this solution is P equals m over 1 plus a e to the negative kmt. So if you see this and you see this, you're like, oh, well, m is 350. I could figure out the initial population by letting t equals to 0, and I know that this number up here is really just km. So I can just set km equal to that number, and if I know m, then I can find k. Again, I don't know what k is, but it's 0.1 divided by 350. Okay? Again, logistic growth. They like to ask some silly calculus questions that confuse you, but they're actually really easy. They ask you limits of the growth rate as t goes to infinity, and the limit of the population as t goes to infinity. Again, that's the definition of the carrying capacity, and eventually the slope is 0. There's no growth because the population reached some carrying capacity. Right? There's nothing wrong with exponential. I didn't mean to hate on exponential. It certainly describes certain things, but it doesn't describe necessarily companies' growth or an economy growth. It doesn't describe a growth of a population over time. It does at the beginning. This is kind of exponential, but really the logistic curve does a much better job of describing things in nature or really even in society. Okay?